Welcome to our channel. Let's begin the journey.
Welcome back to the unstoppable orbit. Today we're diving into a premium explainer on one of the absolute most fundamental mysteries in our physical universe, the unstoppable clockwork of radioactive decay. I mean, if you've ever looked at a massive nuclear power plant, or pondered how we actually date ancient artifacts, or even wondered how the sun just keeps burning, well, it all comes down to the invisible, unrelenting rhythms of unstable atoms.
Okay, here's our roadmap for this explainer. We'll start with the sheer accident that led to the discovery of radioactivity, then break down its three main forms. After that, we'll dive into the radioactive decay law, define half-life versus mean life, look at how we actually measure this stuff with becquerels and curies, and finally, bring it all together by looking at decay heat inside modern nuclear reactors. Let's get into it.
Section 1. The discovery of radioactivity. So, the subatomic world wasn't actually cracked open by some perfectly calculated design. It was pure scientific serendipity. Picture this. It's 1896, and physicist A.H. Becquerel is studying fluorescence. He shines visible light on some uranium potassium sulfate, meticulously wraps it in thick black paper, and sticks a piece of solid silver right between the package and a photographic plate. Fast forward a few hours, he develops the plate, and it's completely blackened. These unseen, highly penetrating emissions had effortlessly punched right through the black paper and the solid silver. Becquerel had accidentally figured out that unstable uranium nuclei just spontaneously disintegrate. They don't need external heat, they don't need pressure, it's a process driven entirely by their own internal instability.
Moving on to Section 2, the three forms of decay.
So an unstable nucleus is basically constantly seeking stability, and it does this through three main pathways. First up, we've got alpha decay. This usually happens in really heavy atoms, where the nucleus just ejects this massive, relatively slow-moving helium nucleus. Then there's beta decay. This is when a nucleus has too many neutrons or protons, so it spits out a lightweight, fast-moving electron or positron to rebalance itself. And finally, gamma decay. This one is pure electromagnetic energy. When a nucleus is in an excited, high-energy state, it just drops down to a lower energy state by radiating a highly penetrating gamma photon. It doesn't actually change its internal atomic structure, it's literally just the nucleus cooling down.
Which brings us to Section 3, the radioactive decay law. Now, here's the ultimate paradox of nuclear physics. If you isolate one single, solitary, unstable atom, it is literally impossible to predict when it's going to decay. It could be in the next microsecond, or it could be a billion years from now. It's totally random. But if you take an immense cluster of them, like a whole mole of atoms, that chaos just evaporates. Suddenly, the entire group follows this strict, unyielding statistical rule. And that rule is defined by this equation, which is basically the mathematical rhythm of the universe, the radioactive decay law. It mathematically proves that the number of remaining undecayed nuclei drops exponentially over time. You've got n sub 0, which is your starting count, and then you have lambda, the decay constant. That's the specific, constant probability of decay for that exact element. And the crazy thing? No external force, no extreme heat, and no amount of pressure can change lambda. It is completely immutable.
When we map this out mathematically, it's wild to see how it works. The short-lived nuclides, the ones with a really large decay constant, just plunge super quickly towards zero. They burn fast and bright. But then you have the perfectly stable elements that don't decay at all, and they just draw a flat horizontal line, forever. The entire clockwork is dictated strictly by that internal probability.
All right, Section 4, half-life and mean life. You've probably heard the term half-life before, right? Half-life, or T1/2, is precisely what it sounds like. It's the exact amount of time it takes for 50% of your radioactive nuclei to just vanish. So, if you start with 1,000,000 atoms, one half-life later, you've got exactly 500,000 left. Give it another half-life and you're down to 250,000. It's an exact, predictable breakdown related directly to the decay constant.
But here's the catch. Half-life is a group measurement. What if you want to calculate the average lifetime of one specific atom, from the moment it's created to the moment it's destroyed? For that, we use mean life, represented by the Greek letter tau. Because of how exponential decay works mathematically speaking, mean life is always exactly 44% longer than the half-life. It might sound like a subtle difference, but it's absolutely crucial when you're engineering real-world nuclear systems.
Section 5, activity. Becquerels and curies.
So knowing how long these atoms live naturally leads to a really practical question. Just how violently are they breaking apart right now? Well, the rate of this spontaneous decay in any given sample is called its activity. To find it, you just multiply that decay constant we talked about by the number of actual nuclei present, totally independent of pressure or temperature. The modern standard unit for this is the becquerel, named after our guy from 1896, and 1 becquerel is incredibly small. It equals exactly 1 single atomic disintegration per second. A typical radioactive source in a lab might be millions of becquerels.
But if you want to truly grasp the staggering, almost terrifying scale of subatomic activity, you've got to look at the older historical unit, the curie. Originally, 1 curie was defined by the activity of just a single gram of radium-226. Just imagine a tiny piece of metal, maybe the size of a paperclip. That 1 single gram unleashes an unbelievable 37 billion disintegrations every single second. It is an absolutely mind-bending density of pure power. Let's wrap it up with Section 6, decay heat in reactors. So why does all this invisible math matter to us? Well, in a nuclear reactor, we don't just sit around passively waiting for atoms to spontaneously decay. We force the issue through a manually induced process called nuclear fission. We take these fuel rods made of enriched uranium, mostly U-238, but containing about 3% of the highly fissile uranium-235, and we purposefully hit them with a slow-moving thermal neutron. The U-235 absorbs that neutron, becomes incredibly unstable, and literally shatters. It violently splinters, spitting out 2 to 3 new fast-moving neutrons and releasing a massive 200 million electron volts of energy per atom. We then use control rods to soak up the extra neutrons and perfectly manage this furious roaring chain reaction. Let's trace that energy flow. That induced fission releases highly penetrating gamma rays, and the sheer kinetic energy of the flying fragments creates intense friction, which generates heat. We pump in cold coolant, like pressurized water or gas, to safely absorb this monumental decay heat right off the fuel rods. Then, that extremely hot coolant is pumped out to boil water, create high-pressure steam, and spin massive turbines. The invisible kinetic energy of a shattered atom gets converted directly into electricity. It's literally powering the grid that lets you watch this explainer right now. It's honestly wild to think about. We started with a fogged-up photographic plate sitting in a dark drawer in 1896 and ended up harnessing the mathematics to power entire civilizations. Which leaves us with a pretty big final thought to ponder. If this exact unstoppable statistical clockwork drives the roaring heart of our reactors and calculates the precise age of our planet, what other invisible mathematical forces are out there, quietly dictating the fate of the universe right now, just waiting for us to accidentally discover them?
The view from here is breathtaking. Command, we are in position and ready for the next phase. If you liked the video, subscribe and comment the topic you want next. Thanks for watching, and stay unstoppable.